In this video, I'm going to present the Fourier transform and derive it from the complex Fourier series. We know that signals or functions can be represented by adding together sinusoidal functions of an infinite range of frequencies. The problem is, up to now, using the Fourier series or the complex Fourier series, is that we've always needed those functions to be real and periodic, or indeed complex and periodic for the case of the complex Fourier series, but it's the periodicity that's been kind of limiting things. So with the Fourier transform, the big move forward is that we now consider functions that no longer need to repeat in time or repeat in space. And so that can be considered really just by allowing a periodic function to have a period that tends towards infinity. So in a sense, they're still periodic, but because the period is now tending to infinity, therefore, in effect, they're not periodic, and that is what the Fourier transform does. It just lets the period tend to infinity and look at that limiting case, thereby handling any function that is no longer required to repeat in time or to repeat in space. So let's take a look at the very familiar Fourier series. We're saying there that a real periodic function can be composed, synthesized by a collection of cosine functions, including cos 0, and a collection of sine functions of increasing frequency. And then we also know that a real periodic function can also be expressed as an infinite sum of complex exponentials with complex coefficients. And the remarkable fact to note here is that even though the right-hand side has complex numbers involved at every single stage, when we add them all together, or rather when we do the multiplication by the coefficient and the complex exponential, add them all together, we still recover a real periodic function if indeed we're doing this complex Fourier series for a real periodic function. But of course, this also now opens up the opportunity to do complex valued periodic functions. So that's fine, but the catch is, as I say, these are for periodic functions, and so now we want to be moving on towards functions that are not periodic. Before we do so, let's just take a look again at the Fourier series. This is a function that's periodic, f of t, in red, and we're saying we can compose it by adding together sines and cosines, as shown in the blue here in this animation from Wikipedia. So there we're seeing that red function decomposed into multiple sinusoidal functions, and then we see that the amount of each one of those functions is given by the coefficients. So here we see both the original function and the coefficients that made up that function, as in the coefficients of the sines and cosines that made up that function. Okay, so those coefficients for the Fourier series, we know that they are found just by taking the real periodic function, multiplying by each cosine for each frequency, doing the definite integral, and dividing by the range of integration, and that gives you the coefficient for each of the cosines present in f of t. We just need to scale that up by a factor of 2 in the Fourier synthesis, because otherwise we'll just have a cos squared here, which when you average that out gives a value of 1/2, and so you need to double that up in the Fourier synthesis in the expression that I'm giving. And the expression that I give is one that allows direct equivalence with this complex Fourier series expression here, or rather this is the analysis equation for the complex Fourier series, where we see this direct equality between the complex coefficients Cn for the complex exponentials that make up f of t, and how those complex coefficients relate to the coefficients for the cosines and the coefficients for the sine functions in the standard Fourier series. So we're familiar, hopefully already from other videos, with these expressions for finding the Fourier coefficients. Now, to develop the Fourier transform, we're going to start with the expression for finding the coefficients for the complex Fourier series. So here we are with the periodic function f of t multiplied by e to the minus in omega naught t in order to find the coefficient Cn for e to the plus in omega naught t. And of course, it's not just a multiplication, we need to do the summation, the integration, as well as the division by the range of integration. Now, what we're going to do then is let the period t tend to infinity in order to look at these coefficients for the case of functions which are not periodic. In other words, if that period tends to infinity, then effectively the function is not periodic. Now to do that, if t is tending towards infinity here, then it would look like this expression on the right-hand side would tend to 0. So to prevent that, what we do is multiply both sides by the period t. So that removes that division by the period t here. And instead, we now have a value here, t that's tending to infinity, that's now multiplied by Cn, which you can see from this original expression was tending to 0. So those, if you like, balance each other out, and we end up with a finite complex number on the left-hand side of this expression, which is obviously a desirable thing to have rather than a value that's tending to 0 or a value that's shooting up to infinity. Okay, so if we do that, and if we remember that omega 0 for the complex Fourier series and for the regular Fourier series was equal to 2 pi divided by t, it should be clear that as t tends to infinity, if we look at this expression on the left-hand side, as t tends to infinity, so omega 0 tends to something very small indeed, such that when we multiply that very small quantity omega 0, that fundamental frequency effectively is tending to 0. When we multiply it by integer values n, and remember those integer values go from minus infinity to plus infinity, got infinitely many of them, then even if omega 0 is absolutely tiny, we effectively end up with a continuous variable from minus infinity to plus infinity, which we will label as the frequency omega. So as you can see here, we're saying that we've got a complex value f, which is representing that tcn, and that's a function now of continuous frequency omega. So if you see this expression, we can see that before we had discrete counting indices n for each of the frequencies. These were all coefficients these were all multipliers of omega 0. And now that n omega 0 is now being replaced by a continuous variable omega in this expression for the Fourier transform. So the dt stays the same, the f of t stays the same, the period has tended to infinity, so the minus t over 2 to plus t over 2 has now become minus infinity to plus infinity. And then the other changes are the one we've pointed out, which is tcn. We have a dependency on n, which is now reflected by a dependency on omega here. And then tc, c was a complex number, t was the period. They're just multiplied together to give an overall complex value f. So this is a complex valued function f, which is a function of the frequency omega, and that frequency omega is a continuous variable which has arisen from using what originally were integer multiples of omega 0, and because that omega 0 has become so small, integer multiples of something very small effectively gives us a continuous range of omega values, which is exactly what we see in the Fourier transform. So that Fourier transform will be giving us a complex value f as a function of frequency omega. So we know full well from the complex Fourier series expressions that we've gone over before that having derived f from Cn, we know that we're going to have this form of a and b, where a, if you like, corresponds to the coefficients for the cosine functions. So this, if you like, is like a cosine transform, and b correspond to those coefficients for the sine functions. And so what we have here is like a sine transform. So on the left-hand side, I've got the standard Fourier transform that you just saw on the previous slide. And all I've done is use Euler's formula here to re-express this complex exponential, which is e to the minus I omega t, to re-express that as cos omega t minus I sine omega t. So you can easily see how we get this just by expanding that complex exponential into its separate real and imaginary components. And that's why we see, effectively, we've got a cosine transform and a sine transform. Alternatively, as we know, we could represent this complex quantity not just as the form of real plus imaginary, but we could also express it in terms of amplitude or magnitude and phase on the complex plane as well. So therefore, we could regard this as giving us the amplitude or the magnitude of a cosine function of a particular frequency and with a particular phase shift. So let's now look at the inverse Fourier transform. We start with the complex Fourier series. So this is the expression that we've seen before for a periodic function f as a function of time t, given by an infinite summation of complex coefficients multiplied by complex exponentials. What we will do is consider what we've previously done for finding the Fourier transform, which was to let t tend to infinity. And you'll recall from the previous slides that we ended up with this expression where we were saying that f of omega, the complex value found from the Fourier transform as a function of continuous frequency omega, was found by taking the original period t and multiplying it by the complex coefficient for frequency n, which was Cn. So we can take that and substitute it into the complex Fourier series expression. So we can see that Cn is going to be f of omega divided by t. And that's exactly what we've done here. Everything else has stayed the same. I've just replaced c of n by f of omega divided by t, based on the earlier slides. Now, as we know again, t, the fundamental period, is related to a fundamental frequency omega using this relation with the 2 pi involved. So we're just going to substitute that into this expression now. So t is equal to 2 pi divided by omega 0. So that gives us a 2 pi in the denominator here, because t is in the denominator. And then we've got an omega 0 up in the numerator here. So that's all we've done to get to this line. And then again, we recognize that as t tends to infinity, so omega 0 becomes very small. And yet again, then we are replacing integer multiples n of this small quantity omega 0, we're replacing that by a continuous variable omega. Then also we've got an original omega 0 still here, and that also then becomes an infinitesimally small element d omega as part of this integral equation. And then we have this scaling factor 1 over 2 pi in the front. So that is how we get the expression for the inverse Fourier transform. And then I've just put a little note at the bottom here saying that really the difference between the inverse Fourier transform and the complex Fourier series is that, of course, we're just dealing with a continuous frequency omega now, rather than the discrete n omega 0, which we've been dealing with before in the Fourier series. And that has arisen from the fact of letting the period now tend to infinity. So, it's important to notice here that when we deal with Fourier series, we often talk about the Fourier series and the complex Fourier series. But when we talk about the Fourier transform, we talk about the Fourier transform. But notice those are not obvious pairings. We have, in the slides shown before, we have derived the Fourier transform from the equations used to find the coefficients for the Fourier series. Okay? And likewise here, by starting with the Fourier series or the complex Fourier series, we've derived the inverse Fourier transform. So the inverse Fourier transform is really the direct analogy with the complex Fourier series or the Fourier series, because that's the Fourier synthesis equation, where we're saying express some function f of t as an infinite summation of sines and cosines. That's what the Fourier series does, that's what the complex Fourier series does, and that is what the inverse Fourier transform does. When we're trying to find the amounts of the frequencies, that's when we would use the Fourier transform, or by analogy with the Fourier series and the complex Fourier series, we would use the analysis equations that give us the coefficients. So in review then, signals, as we know, can be represented by adding together sinusoidal basis functions, sines and cosines, or complex exponentials. Up to now, we've been requiring them to be periodic signals. In other words, the signals that we're representing, we've required those to be periodic. And the Fourier transform and the inverse Fourier transform now allow us to consider functions which are no longer required to be periodic. So in another video, we'll go into some examples of the Fourier transform. Thanks for listening.